All right, in this section, we'll look at linear equations and absolute value inequalities. And out of this section, we're going to be using interval notation. We're going to be finding the intersections and unions of intervals. Also, we'll be solving linear inequalities, recognizing inequalities with no solution or all real numbers as solutions. Also, we'll be solving compound inequalities and absolute value inequalities. So we have a lot of ground to cover in this particular section. All right, on this particular sheet, I have the interval notation, and there are 4 types. One of them is the open interval, and the open interval always has the parentheses around the a and the b. That represents the set of all real numbers between but not including a and b. So set builder notation would be a comma b, with the parentheses for open interval, and that's the set of all x such that x is greater than a and less than b. And the graph will look like this. Here you have at a and b, you'll have parentheses around the a and the b, and everything shaded in between, meaning that all of the values of x are between a and b, with the exception of a and b. And then the opposite of an open interval is the closed interval. This one has brackets in it. That's the set of all real numbers between a and b, and it does include a and b. So here in this case, it would be the set of all x such that x is greater than or equal to a and less than or equal to b. So here you'll have a comma b with the brackets around the a and the b. And the notation, if you were to graph this, there will be brackets, a left bracket at a and a right bracket at b, and it's shaded in between, showing all the values of x are between a and b, and it does include a and b. All right, next we'll look at the infinite interval, and there are 2 types. One of them is from a to infinity. The one on the top represents from a to positive infinity. That represents the set of all real numbers that are greater than a. And by the way, the infinity symbol is just a symbol. It looks like a number 8 tilted on its side. Okay, it doesn't represent a real number. It indicates that the interval extends indefinitely to the right. So that means it goes on and on to the right without end. Okay, so here with a comma infinity, where a is open with the parentheses, that's showing that the values of x such that x is greater than a. And the way we graph that is we use a left parentheses at a and shade everything to the right. It goes on and on and on without end. And another infinite interval would be like from negative infinity up to b, which includes b, and here we have the bracket here, for example. This represents the set of all real numbers that are less than or equal to b. Okay, that's what this means. And again, it goes on and on and on indefinitely to the left. So here, if we were to graph this, a bracket would be at b to show that b is included in that solution set, and then we shade everything to the left indefinitely, because it's negative infinity. So a positive infinity is going to be to the right, shaded indefinitely, or extended indefinitely. Negative infinity is going to be to the left, and it extends indefinitely to the left. All right, this next sheet has the parentheses and brackets in interval notation. Parentheses indicate that the endpoints are not included in any interval. The square brackets indicate that the endpoints are included in that interval. And this right here, this table represents the interval notation and the set builder notation and its graph. That first one is from a to b, where a and b are not included. That's the set of all x values such that x is greater than a and less than b. So you use open parentheses around for the a and the b, and then shade in between. And then the closed bracket, which is the second one, AB. That's the set of all x such that x is greater than a and less than or equal to b. You'll use square brackets at a and b and shade in between. You might have a half open or a half closed interval, where in this case here, the values of x are bigger than a, well, greater than or equal to a, and less than b. So at a it'll be a left parentheses, but at b it'll be, left bracket, but at b it'll be a right parentheses. And on this one, the other way around, the left parentheses could be at a and the right parentheses could be at b. And then the next one are the infinity, from a to infinity, meaning that x is greater than a, so left parentheses at a shaded indefinitely to the right. Closed bracket at a means that a is included, so that means you'll use a closed bracket at a and it's shaded indefinitely to the right. And then these two front represent negative infinity to that number. From negative infinity to b, where b is not included, you'll use a right parentheses and shade everything indefinitely to the left. From negative infinity to b, where b is included, you'll use the bracket and shade everything to the left. And then from negative infinity to infinity, that's the set of all real numbers. Or the set of all x, where x is a real number. That's going to be the entire number line. You'll shade indefinitely to the left and to the right. Okay. All right, now let's look at how we can graph interval notation. In this case here, we'll start with part A, which is -2, 5. And notice how this is written. You have a bracket at -2 and a parentheses at 5. The bracket at -2 means that 2 is included. -2 is included. But for 5, it's not included. So if we were to graph this on a number line, here's -2, and here's 5. I'm going to use different colored ink here. In this case here, we're going to put a bracket at -2 to show that -2 is included in this interval. But for 5, it has the parentheses, so we're going to use a right parentheses at 5 to show that 5 will not be included. Now we're going to shade in between because we want to show that all the values of x are between -2 and 5. Because that's basically what that interval means, if we were to write that in set builder notation. Okay, that's the set of all x such that x is greater than or equal to -2 and less than 5. So that's basically what that interval means. And that's what the graph would look like. Okay, now on to part B, we have a closed interval from 1 to 3.5. 1 to 3.5. And notice that we have brackets at both 1 and 3.5. So here's how we'll graph this. All right, at 1, we're going to have a left square bracket because 1 is included. 3.5 is included as well. Now 3.5 is halfway between 3 and 4, so here's 3.5 right here. And we're going to use a closed bracket here as well. And then we'll shade in between those two to show that all the values of x are between -1 and 3.5. And we do include 1 and 3.5 as well. Okay, now part C, we have this, -infinity to -1. -infinity to -1. And we want to graph this interval. Now, this is an infinity. It goes to the left indefinitely. So at -1 is not included. We use a right parentheses here to show that -1 is not included. And we shade everything to the left of -1 to show that this goes on indefinitely. Okay, so that's how we graph intervals that are written in interval notation. Okay. All right, now the next thing we'll look at is intersections and unions of intervals. Okay. We have a procedure that we can use. We're going to graph each interval on the number line. And then to find the intersection, you're going to take the portion of the number line that the two graphs have in common. In other words, you want to find out at what place do these two graphs overlap. And then to find the union, which is part B, you're going to take the portion of the number line representing the total collection of the numbers in the two graphs. That means you're going to merge the two graphs together. That's what union means. You're going to put the two graphs together. With the intersection, you want to find where these two overlap. Like in this particular situation here, for the intersection, you got the ordered pair, well, you got the interval 1, 4. Notice that we have left parentheses at 1 and the right parentheses at 4 to show that 1 and 4 are not included, and we shade in between. And then the interval 2, 8, where the 2 and the 8 are included, you have to close parentheses, square brackets. So we use square brackets at 2 and 8 and shade in between. Now we want to find out where these two overlap. Well, the overlap starts between 2 and 4. Okay? Now notice in this graph the 2 is included, but in this one the 2 is not included. So that's why we use, well, it's included as well. That's why we use brackets here, because 2 is included in both of these. But for the 4, it's included in one, but not this first one. So that's why we use parentheses. Okay? For you to use the closed bracket when you're doing the intersection, that number must be included in both of them. Okay? So in this case, the 2 is included in both of these graphs, so the intersection would be at 2 and 4, where the 4 is not included. So that's how we write like this: 2, 4, with the 2 having the left bracket and the 4 having the right parentheses. Okay. Now for the union, you're just going to put the two together. Like this one. For 1, 4, of course, left parentheses at 1, right parentheses at 4 shaded in between. And for 2, 8, where 2 and 8 are included, left bracket at 2, right bracket at 8, and you shade them in between. Now we're going to put the two together. The one farthest to the left is 1, and it's not included, so you'll use the left parentheses. Farthest to the right is 8. We'll use that and use brackets there. Okay, so we're joining these two together. So the union of the interval 1, 4, open interval 1, 4, and the closed interval 2, 8 would be the half closed, half open interval 1, 8. So basically, we're just merging the two together, the two graphs together, to come up with one. Let's look at another example of that. Here's a couple of examples that are like this. Take a look at part A. Here you're going to find each set. In part A, you got the closed interval 1, 3, and you're finding the intersection of the open interval 2, 6. And by the way, the upside down U represents the intersection. The U itself represents the union. That's the difference. This is the intersection. This is the union. We're first finding the intersection of these two graphs. Let's graph each one of these individually. and see what they look like. For 1, 3, we're going to draw a number line. And in this case here, for 1, 3, we're going to use the left bracket of 1 because of the bracket here. And the 3 has a bracket as well, so we use a right bracket here. And we're going to shade in between to show that all of the numbers between 1 and 3 are included. And then for 2, 6, this one is an open interval. Now I might need to extend this a bit so that you can see where these two overlap, because we're dealing with the intersection here. Alright, now for 2, 6, they're both open because it is an open interval because it has parentheses. So we're going to use a left parentheses at 2 and a right parentheses at 6, and then we're going to shade in between. So that's the graph of the open interval 2, 6. Now we want to find the intersection of those two. So this is 1, 3, intersection 2, 6. Now notice, if you were to look at this, you're going to see an overlap between 2 and 3. Now, we need to find out whether we're going to use brackets or parentheses. If it's included in both of them, we're going to use brackets. If it's included in only one of them, then we're going to use parentheses. In this case, the 2 is only included in this one, but not in this second interval. So we have to use parentheses. For 3, it's included in both of them. So we use brackets. And then we shade in between 2 and 3. Okay. So that intersection would be this open interval, well, half open, half closed interval, 2, 3. Okay. So that's how we use the intersection of intervals in this case. All right, now that was part A. Now part B deals with the union. That's putting the two together. I'm going to do this one down here. It's the same two intervals, but this time we're going to do the union of those two graphs. Okay, now I've already got the graphs already done here for 1, 3, and 2, 6. Now I just want to put the two together. Just merge the two. Okay, by looking at these two, I take the one that's farthest to the left of either one of these two. The one that's farthest to the left is at 1. And it has a bracket, so I use a left bracket here. The one farthest to the right is the one that I will use. Of these two, the farthest to the right is a 6, and it has a right parentheses here. So I use the right parentheses at 6. And then shade everything in between. Okay. So that represents the union of the closed interval 1, 3 and the open interval 2, 6, which will look like this. And it's going to be this interval, or half open, half closed, half open interval 1, 6. Okay. So that's how you find the intersection and the union of two intervals. Okay. Now the next thing we're going to look at is how to solve linear inequalities in one variable. Solving linear inequalities in one variable. When we solve an inequality, we're dealing with the process of finding the set of real numbers or set of numbers or solutions that will make the inequality a true statement. And the set of all solutions is called the solution set of the inequality. Set builder notation and interval notation are used to represent solution sets. Okay, so here we're going to be using set builder notation and more than likely interval notation as well. Now, there's one rule that you need to know when you solve a linear inequality, and that is when we multiply or divide both sides of an inequality by a negative number, the direction of the inequality symbol is reversed. Okay, so here you reverse your inequality symbol only when you divide or multiply both sides by a negative number, and that's only in a linear inequality. And on this next sheet is the properties of inequalities. There are three types. One of them is the addition property, which is quite easy because if you add or subtract the same number on both sides of an inequality, that symbol stays the same. And if it's a positive number, when you're multiplying or dividing by a positive number, that inequality stays the same. But it's only when you're multiplying or dividing both sides of an inequality by the same negative quantity. That's where your inequality symbol stays, your inequality symbol reverses. Okay? So like in this case here we have negative 4x is less than 20. When you divide both sides by negative 4, that greater than symbol changes, less than symbol changes to greater than. So you'll have x is greater than negative 5. Okay. Now we're going to look at these properties with some of these problems here. Let's say we want to solve and graph the solution set on a number line. So here you're going to have 2 minus 3x is less than or equal to 5. 2 minus 3x is less than or equal to 5. Alright, let's first get the x by itself. We need to get rid of the 2 that's in front of it. And we're going to have to subtract 2 on both sides. So this inequality. So now you're going to have negative 3x. Don't forget about that minus sign in front of that 3x. That's negative 3x. Is less than or equal to 3. And then to get the x by itself, you're going to divide both sides by negative 3. Now keep in mind, we're dividing both sides by a negative number, so that means less than or equal to will change to greater than or equal to. And then 3 divided by negative 3 is negative 1. So your inequality will be x is greater than or equal to negative 1. And we're going to graph this solution set on the number line. Here's 0. Here's negative 1. Now the way we're going to do that is this. It's greater than, and negative 1 is included, so we're going to use the left bracket. Notice that the inequality symbol is pointing to the right. So that means we always shade to the right of negative 1 in this case. Okay. That's what the graph looks like. Now, interval notation, of course, would be from negative 1, and it goes on indefinitely to the right, so we use positive infinity. And keep in mind, for positive infinity and negative infinity, we always use parentheses to show that infinity, positive or negative, goes on to the left or to the right indefinitely without end. Okay, let's look at another example. Let's say we had this. 3x plus 1 is greater than 7x minus 15. (3x plus 1 is greater than 7x minus 15. We're going to solve this inequality and graph the solution set on the number line. And we're going to write this in interval notation, by the way. So 3x plus 1 is greater than 7x minus 15. The easy way to do this is put the variable on the left-hand side when you're solving an inequality. So I'm going to move the 7x over to where the 3x is. by subtracting 7x on both sides. So now 3x minus 7x is negative 4x plus 1 is greater than negative 15. And don't forget about that minus sign in front of the 15. That's negative 15. Now we want to get the negative 4x by itself. We're adding 1, so we need to subtract 1 on both sides. So now you have negative 4x is greater than negative 16. And then divide both sides by negative 4. Now, again, we're dividing by a negative in this inequality, so that means this inequality symbol reverses from greater than to less than. So the x is less than 4. Okay. Now, let's graph this on the number line. Okay, now notice the inequality symbol is pointing to the left, so we know we're going to have to shade to the left of 4. Now notice that 4 is not included because it just says less than. So at 4, we're going to draw a right parentheses there. And then we shade everything to the left of negative 4. And this goes on indefinitely. So my solution set would be negative infinity because it's shaded to the left, so it's negative infinity up to 4. And I'm using right parentheses showing that the 4 is not included in this solution set. Okay. All right, the next thing we're going to look at, well, here's another example of a linear inequality. Now, this one has numbers in the denominator. This pretty much is similar to the ones that had linear equations that have fractions in it. In this case here, we got x minus 4 divided by 2 is greater than or equal to x minus 2 divided by 3 plus 5, 6. And here we want to solve this particular just this inequality. Okay, now, like a linear equation, we want to get rid of these numbers that are in the denominator by multiplying by a least common denominator of 2, 3, and 6, which is, of course, 6. So what we're going to do here is multiply each and every term in this inequality by 6. Okay. As you can see, each inequality will be multiplied by, well, each term in that inequality will be multiplied by 6. Now, this first term, if I divide 2 into 6, it's going to go 3 times. So I'm going to have 3 parentheses, x minus 4 is greater than or equal to, divide 3 into 6, that'll go 2 times. So it'll be 2 parentheses, x minus 2. And then plus these 6's divide out, you're going to be left with 5. So we have 3 parentheses, x minus 4 is greater than 2 parentheses, x minus 2 plus 5. Now let's remove the parentheses and combine like terms. On the left side, if I do 3 times x, that's going to give me 3x minus 3 times 4, that's 12, is greater than or equal to. Now 2 times x, that's 2x, minus 2 times 2, that's going to give me 4. Then bring down the plus 5. Now let's combine like terms on this side right here. Negative 4 plus 5, that's going to give me a plus 1. So now you'll have 3x minus 12 is greater than or equal to 2x plus 1. And then get the x's on one side of the equation, preferably on the left-hand side. We'll subtract 2x on both sides. So that means 3x minus 2x, that's going to leave me with x, then minus 12 is greater than or equal to 1. And then add 12 to both sides. to get the x by itself. So that means x is greater than or equal to 13. So my solution set is this inequality: x is greater than or equal to 13. Now the next step would be to graph this on a number line. Let's say 13 is about right here. And in this case here, 13 is included, so I know I'm going to use brackets. It's pointing to the right, so, well, the inequality symbol is pointing to the right. So I know I'm going to shade to the right of 13. So I'm going to use a left bracket at 13, and then shade to the right. And this goes on indefinitely. And the interval notation for that is this. I'm using a left bracket to show that 13 is included, and it's greater than or equal to, so you have to use positive infinity. That would be interval notation for x is greater than or equal to 13. Bracket at 13 and then infinity. Okay, so this is pretty much how you'll solve another type of inequality. Okay, now let's say we have inequalities that have unusual solution sets. If you make an attempt to solve an inequality that has no solution, what's going to happen is you're going to eliminate the variable and obtain a false statement, such as in this case, 0 is greater than 1. Or if you attempt to solve an inequality that is true for all real numbers, you're going to eliminate the variable and obtain a true statement like 0 is less than 1. So you might get a situation where your inequality may have no solution, or it might be the set of all real numbers. And here's a couple of examples that are just like that, like this one. We'll look at part A, where you have 3 times the quantity x plus 1 is greater than 3x plus 2. Okay, we're going to attempt to solve this particular inequality. The left side, you have to remove the parentheses using the distributive property. So 3 times x, that's 3x, plus 3 times 1, that's going to give you 3. That's greater than 3x plus 2. Now the next step is to get the x's on one side. Now watch what happens when I subtract 3x from both sides. On this side, the 3x's are gone. This side, the 3x's are gone. I got 3 is greater than 2, which is a true statement because 3 is greater than 2. So that means my solution set is going to be the set of all x such that x is a real number. Now that's set builder notation. Now interval notation would just be the entire number line from negative infinity to infinity. And if you were to graph this, you'll have to shade the entire number line indefinitely from left to right, on the left and to the right. Now look at part B. You got x plus 1 is less than or equal to x minus 1. Now, let's try to solve this particular inequality. Now, watch what happens when I try to get the x's on one side by subtracting x on both sides. Those x's are gone on the left side and on the right side. I'm going to end up with 1 is less than or equal to negative 1. So in this case here, this is a false statement because 1 is not less than or equal to negative 1. So that means that this particular inequality has no solution. And sometimes they use this symbol, a circle with a slash showing the empty set, meaning no solution. So here that particular inequality will have no solution. Okay, we'll move on to compound inequalities. This is going to set the stage for something else I'm going to talk about. All right, for a compound inequality, it consists of two inequalities expressed in shorter form with the intersection being implied. Okay, we talked about what intersections were earlier in this video. So here, the intersection that's being implied would be a compound inequality. You're putting the two inequalities together, and it's written in a shorter form, like -3 is less than 2x plus 1, and 2x plus 1 is less than or equal to 3, can be written this way as a compound inequality. And we can appropriately read this as 2x plus 1 is greater than -3 and less than or equal to 3. That's how we appropriately read a compound inequality. And when we solve a compound inequality, we're going to perform the same operation on all three parts of the inequality in order to isolate the variable in the middle. Our objective is to get that variable by itself in the middle when we're dealing with a compound inequality. And let's look at this particular example. Here we want to solve and graph the solution set on the number line, and we're going to write this in interval notation as well. Now if you want to read this left to right, you can say 1 is less than or equal to 2x plus 3 is less than 11. We correctly read this as 2x plus 3 is greater than or equal to 1 and less than 11. Now here we want to solve this particular compound inequality. So in this case here, we want to get this x by itself in the middle. So here, the opposite of adding 3 is subtracting 3. So on the left side of this inequality, we're going to subtract 3. In the middle, we're going to subtract 3. And also on the right side, we have to subtract 3. Okay? We're subtracting 3 on the left side, in the middle, and on the right side of this compound inequality. So here we're going to have 1 minus 3, that's -2. That's less than 2x, less than 11 minus 3, which is 8. And then we still got to get the x by itself. It's being multiplied by 2. So on the left side, and in the middle, and on the right side, we're going to divide by 2. The left side is -2 divided by 2. That's -1. Less than or equal to x, less than 8 divided by 2 is 4. So we have -1 is less than or equal to x, less than or equal to 4, meaning that x is greater than or equal to 1 and less than 4. The interval notation is this. The -1 has the less than or equal to symbol, so we use a left bracket for -1. The 4 only has less than, so we use right parentheses. That's the interval notation. Here's the graph of that. At -1 is a left bracket, and at 4 is going to be a right parentheses. And we shade everything in between -1 and 4 to show that the values of x are between -1 and 4, and only including -1. Okay, so that's pretty much how you will solve a compound inequality for this particular situation. Okay. Now, the last thing we'll talk about is how to solve absolute value inequalities. Because the part where you're dealing with compound inequalities, this also is involving the part where you have to solve an absolute value inequality. Okay, so here's how we solve an absolute value inequality. If capital X is an algebraic expression and C is a positive number, then you can have two situations. Absolute value of X is less than C can be written as this. X is greater than -C and less than C. This part you write as a compound inequality. With absolute value being less than a constant, you will write this as a compound inequality. Now, if you have greater than in an absolute value, in this case, absolute value of x is greater than c, this you'll write as two separate inequalities. One of them will be the obvious x is greater than c. The second one will be x is less than negative c. That second inequality, you'll reverse the inequality symbol to the opposite and change the sign of that constant to a negative. Okay? And these rules also apply if you had less than or equal to or greater than or equal to. Okay? And we're going to look at some examples that are like that. Take a look at this one. X minus 2 is less than, well, absolute value of x minus 2 is less than 5. Absolute value of x minus 2 is less than 5. Now, keep in mind the inequality is going to tell you which procedure you're going to need to write this particular absolute value inequality. In this case, we have less than. So that means we need to write this as a compound inequality. Like number 1 right here. Absolute value of x is less than c. We have to write it in this particular format as a compound inequality. Negative c is less than x and less than c. Okay, so here's with this less than, the x minus 2 goes in the middle of your two less than symbols. On the left side, the 5 becomes negative, and on the right side, the 5 is positive. So here I'm just using this format. Absolute value of x less than c means this. The x is between the less than symbols. The constant is negative on the left side, and the constant is positive on the right side. I'm just applying this particular rule to this particular problem. And here I have to write this as a compound inequality. Now I'm going to go ahead and get the x by itself. I'm subtracting 2, so I need to add 2 on all three parts of this compound inequality. So now, negative 5 plus 2, that's negative 3, is less than x. It's less than 5 plus 2, which is 7. So negative 3 is less than x and less than 7. Now, interval notation, of course, they're both going to have parentheses because they're both less than. My two endpoints are negative 3 and 7. And the number line will look like this. Let's say negative 3 is here and 7 is here. And the graph, you'll have a left parentheses at negative 3, and a right parentheses at 7. We're going to shade in between to show that that the values of x are between negative 3 and 7. And it doesn't include those endpoints. Okay, so that's basically how you'll solve an absolute value inequality, like this one. And there are some cases where you might have to get the absolute value inequality by itself. Like in this particular situation here, we got negative 3 times the absolute value of 5x minus 2, and then plus 20 is greater than or equal to negative 19. Okay, so the first thing we need to do here in this problem is get the absolute value of 5x minus 2 by itself before we find out how we're going to write this absolute value inequality. Let's get rid of the plus 20. We need to subtract 20 on both sides. So now you got negative 3 times the absolute value of 5x minus 2 is greater than or equal to, now negative 19 minus 20 is negative 39. Now we still got to get rid of that negative 3 that's in front of the absolute value of 5x minus 2. We need to divide both sides by 3. Now when we divide both sides by a negative number in an inequality, this changes from greater than or equal to less than or equal to. So now you're going to have the absolute value of 5x minus 2 is less than or equal to 13. Okay, now we're going to look at our inequality symbol to determine how we're going to write this. It's less than or equal to. That means we need to write this absolute value inequality as a compound inequality, which means this. The 5x minus 2 goes in the middle of less than or equal to. The 13 on the left side becomes negative. The 13 on the right side becomes positive. And then we're going to solve this compound inequality. So here, we're going to have to add 2 on both sides. Well, on all 3 sides of this compound inequality. All 3 parts. The left side, the middle, and the right side. So here, negative 13 plus 2 is negative 11. That's less than or equal to 5x, less than or equal to 15. And then we're going to divide all 3 parts of this compound inequality by 5. And what I'm going to do here is leave this as negative 11/5, less than or equal to x, less than or equal to 3. So that's my solution to this particular inequality. And the interval notation for that would be, and this is going to be in brackets, not parentheses, because it's less than or equal to negative 11/5 and 3. Now let's look at the graph of that. Negative 11/5 is like negative 2.2. So I'm going to go to the left 2 and about 1/5 of the way past negative 2, which will put it about right here. And it's going to be a left bracket here. And at 3 is going to be a right bracket here. And then we're going to shade in between. That's to show that all the values of x are between negative 11/5 and 3, and it does include those 2 endpoints. Okay, so just like an absolute value equation, you have to get the absolute value symbol by itself before you can start writing it either as a compound inequality or 2 separate inequalities. Okay, and I do believe I have time for one more. This one. Let's say we have 18 is less than the absolute value of 6 minus 3x. Here we're going to solve this and graph the solution set on the number line. 18 is less than 6 minus, 18 is less than the absolute value of 6 minus 3x. Okay, it would be much easier to have the absolute value on the left-hand side of this inequality. So when I change this around, this is what I'm going to have. Absolute value of 6 minus 3x is greater than 18. Now you'll have to think of the fact that if I say 12 is less than 19, if I switch these around, it'll be 19 is greater than 12. I'm switching the inequality symbol. I'm doing the same thing here. 18 is less than 6. The absolute value of 6 minus 3x is the same as saying the absolute value of 6 minus 3x is greater than 18. Okay, now what I need to do here is look at my inequality symbol for this absolute value. It's greater than. I need to write this as 2 separate inequalities. The first inequality will be 6 minus 3x is greater than 18. Now my second inequality is going to be this 6 minus 3x, but this inequality symbol will change from greater than to less than. The 18 changes to negative 18. With greater than or equal to in an absolute value inequality, I must write this as 2 separate inequalities. Now for each inequality, I'm going to get the x by itself. So for 6 minus 3x is greater than 18, if I subtract 6 on both sides, I'm going to have negative 3x is greater than 12. And then divide both sides by negative 3. Now what's going to happen is I'm dividing both sides of this inequality by a negative number. This changes from greater than to less than. And this will be negative 4. So I'll have x is less than negative 4. Then or, for this one right here, 6 minus 3x is less than negative 18. Subtract 6. You're going to get negative 3x is less than negative 24. Then divide both sides by negative 3. That means that x is, now this time, again, I'm dividing both sides of the inequality by a negative. This changes from less than to greater than 8. So my solution will be x is less than negative 4 or x is greater than 8. And here's how we'll graph this on the number line. Now I'm going to show you the interval notation. Here's negative 4. 8 would be over here. Now, anything less than means it's going to be shaded to the left of that number. So at negative 4, I'm going to use a right parentheses here. And if the inequality symbol points to the left, you shade to the left. So we'll shade everything to the left of negative 4. And then x is greater than 8. Well, anything greater than 8 is going to be shaded to the right of 8. So that means let a right parentheses at 8, showing that 8 is not included. And we shade everything to the right. Now let me show you the interval notation for this. We're looking at the numbers from negative infinity up to negative 4. So that's one interval, negative infinity to negative 4, with the parentheses around both the negative infinity and the negative 4. And this u represents the union of those two, because we're putting the two together. And then this other interval is from 8 to infinity. Okay, so that's how you'll write that in interval notation, because you're putting the two together. Okay, now that's basically how you'll solve absolute value inequalities. Okay, so do be familiar with those. And that will conclude this particular section on linear inequalities and absolute value inequalities.